This is EC, and the Fermi level is, if you draw Fermi level, it is exactly middle of these levels or middle of the band gap. Band gap is this one, right? The energy difference between EC to EV. Okay, this is band gap, middle of the band gap. That means what? What does it mean? Okay, at 0 Kelvin, all energy levels, all energy levels below EF or below Fermi level are filled. Okay, are filled. Okay, so that what does it mean? It is exactly lying middle means all energy levels. Here also some energy levels are there. Okay, these are also some energy levels below the Fermi level. All energy levels are filled. Okay, that means we also discussing from starting onwards at 0 Kelvin. These semiconductors are just like insulators only. All electrons are there, but these electrons are bound to the nucleus. There is no free electron. These are all filled in a valence band only. And above the Fermi level, above the EF, all levels, you can say all energy levels or energy state, whatever you can take, are empty. Okay, this is the meaning of this expression. This is the significance of this expression. The Fermi level is lying middle of the band gap, means at 0 Kelvin, all energy levels below the Fermi level are filled. Okay, above the Fermi level are empty. Okay, the meaning of this one is, so this is the meaning. Okay, so this is we have solved. So after that we have discussed that means, so if you this is 0 Kelvin, suppose if you increase the temperature, what happens? So here in valence band, suppose if you take valence band, this is valence band. Okay, this is conduction band. Okay, so at 0 Kelvin, all electrons are bound to the nucleus, right? These are energy state, many states are there. So if you increase temperature, these bound electrons gain some thermal energy and breaks the bond. And after that, they will overcome this energy gap and they jumped into conduction band. Once they jumped into conduction band, these electrons are free. Because of these free electrons, we are getting some current from the intrinsic semiconductor, or these are showing some conductivity, This is the thing. Okay, now we will see probability density function. That is also we have discussed. Okay, what is mean by what will give this information? What this probability density function gives information? Exponential E minus EF by KT. Okay, this is the Fermi Dirac distribution function. What is what this expression gives information? What information this will give? What information this will give?
The electrons will become free. It will convert valency bond to conduction band electrons when temperature increases.
Okay. Okay, that's correct only, not exactly. That means, so it will express the probability of a state being occupied a electron. Okay, probability of a state being occupied by electron. Okay, or suppose these states are there, we are filling these electrons, some electrons are filling these states. So what is the probability of these electrons occupying these states? Okay, probability of occupancy of electrons in a state, or you can say probability of a state being occupied by electron. This will give the information. Now we will see how these are filling. Okay, how these are filling. Suppose E minus EF much less than KT. What is this one? Much less than KT means very low temperature. Very low temperature. This term f of E becomes 1 by 1 plus e to the power of, what is this value? Minus infinity means what? What is the e to the power of minus infinity? What is the value this one? What is the value of e to the power of minus infinity? Don't know. 0. Okay, if you don't know, okay, no problem, but respond. Okay, 1 by 1 plus 0, that is equal to 0. That means at low temperature, a very low temperature, our energy below the very much lower than the KT. KT value is the 25 milli electron volts. If you substitute K and T, that is at room temperature. This is 25 milli electron volts. This is at room temperature, KT value. Okay. if this E minus EF is much less than KT, the here Fermi level is becomes 1. That means probability of a state being occupied electron is 1. That means there is a probability of all electrons are occupying these states. Where if low temperature means only valence band only, all states are filling. The probability F of E is equal to 1 means what? We are getting 100% probability of being occupied a state or electrons are filling that state. That is the 100% probability. Where this is possible at very low temperature, only electrons filled in the valence band only. That is only we are discussing starting onwards. At low temperature, all electrons are filled in the valence band. These are bound, okay, which these electrons are bound to the nucleus. That is same condition we proved using Fermi Dirac function. Suppose E minus EF much greater than KT. This energy is very high compared to KT. Then same thing, you use Fermi Dirac function 1 by 1 plus here E, this is positive value, so here we will get the e to the power of infinity plus infinity. Then what is this value here? What is the e to the power of infinity value? What is the e to the power of plus infinity? What is the value?
0.
0. Very good. Okay, very good. Okay, 0. That means okay, that 0 inf that is infinity, man, not 0. E to the power of infinity is infinity only. E to the power of minus infinity, that is 0. Okay. So 1 by infinity means what? 1 by infinity means 0, right? 0. So that means what? It is probability is 0. That means what? If you increase high temperature, if you increase the temperature to very high level, almost all energy levels in the valence band, okay, this is valence band, all energy levels, here some electrons are bound to the nucleus. Okay, if you give very high temperature, what happens? These electrons get more energy, sufficient energy, all electrons break the bond and jump into the conduction band. Okay, conduction band. Okay, these states are filled because all electrons jump into the conduction band. So that means what? Probability of occupying these states is 0. There is no electrons are staying in a valence band because these electrons having sufficient thermal energy and jumping into the conduction band. That's why the probability is 0. Probability is 0 if EF much greater than KT. Very high temperature. That means very high temperature. This is the condition. Okay. Now one more case we will see. Okay. Is it clear now up to these two conditions? Is it clear?
Yes, sir.
So if very low temperature means very low temperature means all electrons are filled in the valence band. Okay, and these electrons are bound to the nucleus. Okay, if you increase the temperature, whatever bound electrons break the bonds and jumps into the conduction band becomes free. How they are jumping? Because they are getting lots of energy. Okay, then if E is equal to EF, suppose here also we'll see one more case. E is equal to EF, E is equal to EF and T is not equal to 0 Kelvin. T is not equal to 0 Kelvin. That means we are giving some certain temperature. Okay, we are giving some certain temperature. So what will happen? See, okay, here Fermi Dirac distribution function E is equal 1 by here exponential e to the power of 0. Okay, E minus EF, right? That is becomes 0. Then this value is off. This value is off. So that means off. That means what? Probability is off means, so when theta when the temperature is not equal to 0, that means not 0 Kelvin, where that electrons having some energy. So half of the electrons filled in the conduction band, half of the fill in the valence band. Okay, now we will draw that distribution function, then you will understand. Okay, so this is the, just a minute, half the probability means sum of the T is not equal to 0 here. Okay, here T is not equal to 0. That means electrons are having some energy and some of the electrons are jumping into the conduction band. Okay, that is the meaning of this one. Okay, there is a half probability of filled and half probability of vacancy. Okay, now we will see another, we will draw one, then you clearly understand what is the probability function. Okay, this is very important. So here we are drawing a energy levels and this is energy, some energy here conduction band. Okay, this is conduction band, or you can say conduction band also. This is lowest energy of conduction band EC, and this is highest energy of conduction band EV, and this is valence band. Okay. So if you take Fermi level or Fermi distribution function versus energy, this is x-axis we are taking Fermi distribution function, and y-axis we are taking energy. Okay, y-axis energy. Okay, very high temperature, all electrons are filling in the conduction band, right? Okay, at very low temperature, all electrons are, there is a probability of, this is, suppose if it is Fermi level EF. Okay, if EF, so at 0 Kelvin or very less temperature, low temperature, all states are being filled. Okay, that is one. Okay, that is one. So this is, suppose this is off and this is one. Okay, so this is Fermi Dirac distribution function. We are taking x-axis and y-axis energy. Okay, x-axis energy. Okay, this is just like this one. Okay, f of e, and this is energy. Okay, this is off, this is 0, off, and on. Okay, like that we have taken here. Okay, at very low temperature, this is all electrons are filled here. Okay, so if you increase the temperature, what happens? So some of the electrons filled in the conduction band, some of the electrons leaves in the valence band. Okay, valence band, that is here. If you say this area is indicating a electrons, filled electrons. Okay, here also small area like this area indicates, so area indicates holes in a valence band. Or I can draw a one another diagram to easy way. So just I'm drawing this way. Just a second. So here see, this is conduction band, this is valence band. Okay, so here we are drawing energy versus this one. Okay, so like this. Okay, like this. So that means here if you draw one line, this area, and here also some area like this. This indicates holes filled. Sorry. This is filled electrons in the conduction band. Okay, filled electrons in the conduction band. This is filled holes in the valence band. Filled holes in the valence band. Okay, like that. If you increase temperature, this will increase. This area will increase. This area will decrease. Okay, this area will here also increases because more holes are increasing. Here more electrons are increasing. So that means what? You already we have theoretically discussed here. Okay, that means more, if you increase the more temperature, more number of electrons are I will draw this one diagram on the way, this way also you can draw it. Okay, f of e into a. So at 0 Kelvin, this is the curve. At 0 Kelvin, all electrons are filled in the valence band. If you increase the temperature, so if you increase the temperature like this, okay, if you increase the temperature, this curve will shift like that. Okay, just like this. So this is T1 and this is T2. Okay, here T1 greater than T2 greater than T1. Okay, T2 greater than T1 are. So if you, that means this curve is indicating if you increase the temperature, more number of electrons are filling conduction band. Okay, because electrons are getting energy, breaking the bond and jumping into the conduction band. This probability function mainly indicates if how the electrons are, how the band. If you increase the temperature, how the electrons are jumping into the conduction band. At 0 Kelvin, all electrons are filling valence band only. At higher temperature, these electrons are being into the conduction band. Using this probability density function, we can clearly explain what is the probability of a state being occupied by a electron. Okay, is this clear now, everyone? Okay, and in intrinsic semiconductor, if you take intrinsic semiconductor, only we can increase the conductivity only by increasing the temperature only. If you increase the temperature, more number of electrons, more number of holes created here, and equal number of electrons are created in the conduction band. Okay, conduction band. Or that is, you can draw this way also. Here area in place of in the area view of you can also represent this way also. This is electrons, this is holes. Okay, this is holes and this is electrons. So that is only in intrinsic semiconductor, giving temperature only we can create free holes and free electrons, and Because of these free holes and free electrons, we will get the conductivity from intrinsic semiconductor. Okay, is this clear to everyone? Any doubts here? You can ask, please. Okay. If you have any doubts, only probability distribution function, what is saying, at low temperature, all electrons are filling valence band only. If you increase the temperature, electrons breaking the bonds because they are having sufficient energy and jumping into the conduction band. Okay, like that, what is the probability? This Fermi Dirac function explains. That's it. Okay, and you can draw the curves. Okay, that in words you can draw it. Okay, any doubt?
Sir,
35
once explain this graph, sir.
graph. Okay, okay.
Yes, sir.
So here, see, okay, please mute. I will explain. Okay, suppose. Okay. So here, just a second, I will explain this thing. Okay, Fermi Dirac distribution function, we got three different cases. One is 0, one is 1, one is half, right? So here we will see the as a function of temperature. Here we will take temperature, and here we will take a Fermi Dirac distribution function. At 0 Kelvin, this all states are filled. Suppose this is wait. So just we will draw a bigger diagram, then it is clear to understand. Okay, so here, so I'm drawing again. This is temperature, and this is Fermi Dirac distribution function. So this is 0, and this is half, and this is 1. Okay, we are taking on y-axis. Okay, and temperature on x-axis. Suppose at 0 Kelvin, suppose if you take 0 Kelvin, these all probability is 1. Probability is 1. That means what? Probability is f of e is equal to 1 at 0 Kelvin. This is 1 at 0 Kelvin. That means what? All states are being filled in the valence band only. In the valence band, all states are filling with electrons. These are bound electrons. Okay. Now, if you increase the temperature, what happen? Some this probability distribution function, what happen? Or you can draw this way also. So here you draw it like this. Okay. At moderate temperature, it is becoming half, right? I'm not able to the correct curve. Okay, this one. This is equal to half. Okay, this is half. So that means what? At E is equal to EF, E is equal to EF. That is energy of electrons equal to Fermi level. Energy of electrons is equal to Fermi level. That means half of the, we are getting half probability. F of E is equal to half, right? That means, so there is a chance of half of the electrons are filling valence band, half of the conduction band, or half of the electrons leaving the valence band and filling the conduction band. F of E is equal to half means 1 by 2 means that is half probability. Probability is half. So some of the electrons are occupying conduction band, some of the electrons are occupying valence band equally. That is equal in intrinsic semiconductor. That is half. Okay, suppose even if you increase the temperature further, okay, more number of electrons are occupied in the conduction and more number of occupied in the valence band. Like this, curves are like this. Here, suppose this is 0 Kelvin, and this is 1, this is T2, and this is T3. Here T3 greater than T2 greater than T1. Okay, because T3 is the higher temperature. First 0 Kelvin, these all states are filled in the valence band. Even if you increase the temperature, some of the electrons are occupying the conduction band. Okay, and some of the here you can in the occupied area also you can represent this way also, but you no need to that one. So if you increasing temperature, this area is increasing, right? Here this area is increasing, this area is increasing. Here the area is decreasing. Here this area is decreasing, right? This area also decreasing, you can say this area decreasing. So this is total 1, right? This is total 1. This area is decreasing, this area is increasing if you increasing the temperature, right? So this is up to here, this area is filled, reduced. After that, this area also decreases, right? But here also this area is increasing. So in the conduction band, area is increasing means more number of electrons are filling that conduction band, if you increase the temperature, more number of electrons are filling conduction band. That's why the area in this upper curve area is increasing, lower curve area under curve it's decreasing, right? So that is the meaning. Just nothing here, just only very simple one. If you increase the temperature, electrons in the valence band getting energy and breaking the bonds and jumping into the conduction band. Like that, if you increase the more temperature, more electrons break the bond and jump into the conduction band. Like that, we are getting more number of free electrons in the conduction band, more number of holes in the valence band. Okay, using this curve, we can explain that way. Okay, is this clear now? Any doubt? Still, if you don't understand, also you can ask. Okay.
Yes, sir, understood.
So here see, just I am explaining one more time. So this is at 0 Kelvin. These all electrons are filled. So this is 0 Kelvin. Okay. Now we are increasing. Suppose 27 degrees centigrade. Okay, 27 degrees centigrade. So here the curve is you can draw like this. Okay, like this. That means this curve is reduced to this much. This much area is reduced. That means this much electrons are jumped into the conduction band. Same area you are occupying this area. Okay. And you increase 100 degrees centigrade. Okay. This curve again increasing like this and here also decreasing like this. That means this much area decreased here. Here also this much area increased. That means if you increase the temperature, more number of free electrons available in the conduction band and more number of free holes available in the valence band. Or if you increase the suppose 300 degrees centigrade, like this curve is shifting like this way. Okay, so curve is here in the top side area is increasing, and area is decreasing. Or in other words also you can say here also you can say this area, but if you say this area, here area is decreasing, here also you can increase. Okay, you can say increase also, you can say in terms of holes you can say increase, but here you can say decrease. In terms of holes you can say area increasing here, in terms of electrons area decreasing. Okay, so very simple. If you increase the temperature, upper side area is increasing. That means more number of free electrons are available because the valence band electrons getting thermal energy and breaking the bond and jumping into the conduction band. That is we are using this Fermi-Dirac distribution function. Fermi-Dirac distribution function. Okay, is this clear? Still okay, or is this clear or any doubt? How you can ask. If you don't understand also you can ask. It's not a problem. I can ready to explain in other way. Okay, if you don't understand means we have to explain in other way. Okay, so that is the thing. And suppose here see, this is a conduction band, this is conduction band, this is valence band. So in terms of in band diagram also you can express, if you increase the temperature, here bound electrons are there, right? In the valence band bound electrons are there, this getting energy and jumping into the conduction band. So here free electrons are available. Like that all electrons are jumping into the conduction band. Here these are free electrons. So here they are creating, once they jump into the conduction band, free holes are created in the valence band, available in the valence band. These are free holes, these are free electrons. Like that, if you increase the temperature, electrons in the conduction band increase, holes in the valence band increase. That is only we represented using Fermi-Dirac distribution function. Fermi-Dirac distribution function. Okay. Any doubt still? If you have doubts, you can ask me. I will explain. Okay. Now we'll do the next topic. Any doubts? Is it clear? 35. 35. Are you there?
Yes, sir.
I don't know. Okay. So Now the another topic, that is okay, tomorrow we'll start. Today I will explain here only one small topic. So here we have derived Fermi Dirac sorry, Fermi level, right? Fermi level is, what is the equation? EC plus EV by 2 plus 3 by 4 kT log mh by me, right? Mh by me. This is effective mass. Okay, so this Fermi level is how it is depending on temperature. Its EF is proportional to the temperature, isn't it? If you, this is common term, this is a constant value. So if you take this one, EF is proportional to temperature, isn't it? Can you
Yes,
write?
sir.
Can Fermi level is always proportional to the temperature. Now, using this expression, we will draw a this Fermi curves. Okay. So just a second. So here, so this is conduction band, this is valence band, conduction band and valence band. Okay, this is the Fermi level generally, right? Fermi level generally in a intrinsic semiconductor. So suppose it is EF is proportional to the temperature. Now EF is, we are taking in respect of electrons. So Fermi level, how it will change? If you here we are increasing the temperature, first we will consider in case of electrons. Okay, how the Fermi level will change? Fermi level decrease or increase? How it will shift? Hmm? In case of, we are taking electron, in case of electron, we are considering we are discussing with respect of electron. If you increase the temperature, how this Fermi level will change? How this Fermi level will shift? Lower or upper? Huh? Are you following question or not? EF proportional to T. What we have discussed, if you increase the temperature to semiconductor, what happens?
EF, EF increases. Goes up.
EF increases. So, we have, what we have discussed, if you increase the temperature, here electrons get energy more and force jump into the conduction band. If you increase more, electrons break up and fill in the conduction band. So like that, here free holes available and free electrons are available. So if you take the temperature, towards the conduction band. Case of electrons, so if you holes, this Fermi level goes to the downside. This is for holes. This is for holes, and this is for electrons. So hole density is increasing. Hole density is increasing. Electron density is increasing. If you want to explain with respect to electron, so Fermi level is increasing towards the shifting towards the conduction band, towards shifting the conduction band. Okay, if you take in terms of hole, Fermi level is shifting downside because holes are available, free electrons are available in the valence conduction band. Okay, this is the EF. Okay, this is the EF. If you increase the temperature, okay, this is for electrons and this is for holes. Okay, is this clear now, everyone? So, if you increase the temperature, free holes are yes, Amma, please. Any doubt?
No, sir.
Okay. So here, so if you increase the temperature, you are getting more number of hole electrons in the conduction band. That means Fermi level always indicates the how majority carriers are there. Electrons are majority carriers are available, holes are available. So your level of the free electrons. So if you increase the temperature, if you explain with respect to electron, the Fermi level shift upside. Okay. So same thing and in the holes also available in the valence band if you increase the temperature, or if you increase the temperature, holes also creating in the valence band. That time number of holes available in the valence band, that time this level is shifting down,